Let's get a full screen. There we go. All right, so this is going to be a quick rundown of the topics that are going to be added to our list of considerations going into the second half of the semester. And so I'll do a few problems and we'll get the conversation started. So one of the things we're going to push for is better understanding of our graphs. Some folks have pretty much mastered exponential, logarithmic, sinusoidal even. Not all the practice with the sinusoids, but a number of folks in class have, basically just started to graph linear functions and quadratics. So we got a long way to go as a class to gain some mastery over the graphs that we've been considering. All right. So when you first return, probably introduce just a couple of more early algebra topics. Perpendiculars and parallels. We've been primarily looking at situations like 5x minus 2y equals 18, passing through 4, 7 perpendicular. So we're just going to phrase the questions a little differently, and I'll give you a couple of points, make you find slope, and then do the parallel and perpendicular. So what do we got? 5 to 20, up 15, 3 to 7, 4. So if I want a parallel, it's going to be the same slope, 15 over 4. And if I want it to pass through negative 2, 9, I'm say x plus 2 plus 9. Nothing challenging here that I can see. And of course, if you have the parallel, then you got the perpendicular, and we kind of knew that anyway. What have I got? Oh, I did a different one than that. So minus 4/15 x plus 2 plus 9. All right, so that should only take us 10 seconds. And we're off and running with that topic. Just one more skill. All right, so systems of equations. We've talked about ax plus by equals a constant. And so if we had something like 9 plus 16 equals 25, if 25 remains constant and 9 goes up to 10, then 16's got to become 50. So one number goes up, the other number goes down. So addition is a linear function that's decreasing, and subtraction is one that's increasing. And so we're going to find those points of intersection of two lines. There's a few things that we have to look at here. This is easy to make mistakes on these problems. So 1 plus 2 equals 3, and 2 plus 3 equals 5. If I add these columns up, I get 3 plus 5 equals 8, which is true. So I can add up the columns. I can also multiply one of the linear situations by a constant, and then I can add up, and I still have equality. All right, so how do we use that in order to solve where these two lines intersect? Well, if I add up the columns, I'm not any better off. I've got 13x plus y equals 11. There's an infinite number of solutions to that. So what we do in this situation, this is called the elimination method, is we get rid of one of the columns. And so I built this off of some answers that we already know. So 8 times 1 is 8. Minus 4, 8 minus 4 is 4, and also 5 times 1 is 5. Minus a minus 2, 5 plus 2 is 7. So we already know our answers. What's the quick way to get this? Well, let me multiply the bottom one by 2. Every single thing by 2. We got to be careful. 8x plus 2y equals 4. So what happens? Nicely, one of the columns cancels. I get 18x equals 18. Oh, x equals 1. Okay, and I'll probably, because this takes so long, and I'm asking you so many questions, I'll probably keep your answers integers. Tell you that ahead of time, at least for the early going here. So once you get an integer answer, you can plug it in, and we can look at 5 times 1 is 5, minus what equals 7. Okay, so there's my y. So I can move the minus y to the other side, make it positive, bring the 7 to this side, make it negative, and there's your -2, which is what we knew to begin. So those two questions we will be practicing along with one other linear situation, probably for 3 nights. So I'll do rapid fire 5. I'll give you 5, maybe 3 of these, maybe 3 of these and 3 of these, and then give you a quick quiz each day. Make sure that you're practicing, looking at the videos that I will accompany with these topics. And there's one more here. Let me get my trusty cart. And come on. All righty. So let's close this. Put that there. Let's put this in the trusty cart. Next topic is variation. So y varies directly as x. Y equals kx. K, constant of proportionality. So let's say that x is 2 and y is 6. Y is 6. Well, then we can find k is 3. So y equals 3x. And then if I give you a new number like 4, you can tell me that y is 4. And we'll talk about that more over the course of several days. Inverse variation. Y equals k over x. Okay, so if x was 12, let's make x 2, make this simpler. Y is 6. Did that twice. Y is 6. So you can find k first with these problems. So 6 equals what divided by 2? Okay, you find k is 12. You replace k with the number 12. And then if I give you another number like 4, and 12 divided by 4 is 3. So what's happened? My x's have gotten bigger, my y's have gotten smaller, and we call that varies inversely. And the last one is maybe a combination. And because, again, these are tedious and take some time, I might just say, okay, can you write the equation? I trust you can solve by plugging in the numbers. You've proven you're capable of doing that. So we'll just write, how do you solve for a problem like this? Y varies. You might as well get in the habit of just putting k down. Directly as x and inversely as p squared. And you'd get values for x, y, and p, which would allow you to solve for k, and then you'll get 2 pieces of information. You can solve for the third unknown. All right, so that's 3 things. And the last thing for the linear is we'll start working with algebraic fractions. We'll get some good factoring practice from this. And some folks, unfortunately, because of COVID and not that many great experiences working with math, a lot of teachers kind of skew it, push it to the side. So x squared minus 4, x plus 2, x minus 2, x squared plus 3x, taking out what's common. We're practicing that as well. Times x squared minus x, so x minus 4, x plus 3, I believe. And x minus 4x plus 2. Okay, so we can see that we don't have to do the x minus 4 as they cancel. The x plus 3 and the x plus 3 are going to cancel. X plus 2s are going to cancel. And we end up with x minus 2 over x. Then we'll get some practice with some user-friendly numbers. You know, maybe plugging in a number like 3 might become easy, or maybe 2. So we can get some quick checks to see that numerator times numerator, denominator times denominator. We'll talk more about it. Hopefully we don't have to spend a great deal of time. But so those 4 questions will come your way as a homework. I'll do 3 problems of each type each night, and you'll hopefully have some success on your own. But if not, you'll do it on your own on a scrap piece of paper, and then you'll follow the video and just copy what I do. The last thing I want you doing at night for homework is something wrong, because then I'm teaching you how to do something wrong well. No. All right, so next topic. So after about 3 or 4 days of that practice, we'll turn our attention to solving inequalities, and we can do those the same way each and every time to get a correct answer. But we'll also push the graphical solutions, because it'll help you if you move on to calculus at some point in your high school career. So we'll use number lines. Here's my number line right here. We'll find the critical numbers. How do we find the critical numbers? We'll set these to 0. All right, we practice the factoring. We have not done too well with stating the answers or factoring when I give you more than one line of factoring. So some folks have done this and stopped here. Well, this is an equation. So what are the critical numbers? 0, -1, and positive. Those are the critical numbers. And we'll just try numbers to find out what works and what doesn't. And we'll study, the value of the exponents as to whether we have a sign change or not. I'll change this last line of work a little later. And but these are all going to change signs. So if I pick a number bigger than 1, I put 1,000,000 in here. If I cube 1,000,000 and then I subtract 1,000,000 from it, am I bigger than 0? Absolutely. So you'll find that there are patterns with these problems, and there's also graphs associated. But we've already got our interval notation. These numbers don't work, 1, 0, and -1. They make 0, not numbers that are bigger than 0. So these are real Y values here. 0 is just, think of it as a Y value, and these as X's. Starting to teach, and I don't want to do that right now. I'm just giving you a rundown. So -1 to 0, union 1 to infinity. And of course, we've talked about what happens if we want equals, how we change these to brackets, and it changes everything right now, but just laying out the goods. All right, now what happens if I get this out of here and I make that a squared? Well, you're going to find out that becomes, if that's true, then that's true, and then it's going to change to false and true. And I'll give you one graph here to show that this is a cubic graph. No, I changed it to a quartic, x to the 4. So, okay, got to make some space here. So 1, I make a dot, so there is not going to be a sign change. There will be at 0, and there will be 1 at -1. And I know that if I put a really big number in here, I get a positive, positive, positive. So we've got a graph that looks like that. And when would this be greater than or equal to 0? Let's look at that right now. From the graphical standpoint, I can see -infinity to -1, and -1 works. Union 0 to infinity, and 0 works. And if I make a careless error here, you can let me know in the comments, because I'm just going to keep going on down the line. All right, so what are the critical numbers here? I will not do this one graphically. I'm not sure what that looks like graphically, and if I don't know what it looks like, you don't have to either. So -7 is critical, +5 is critical, and I just try numbers here. So let's see. Oh, domain. Can I use the numbers or not? Right, so we're using this kind of number line technique to answer some different types of questions. So can I use the number bigger than 5? Okay, well, pick a number bigger than 5. Let's put 6 in. 5 minus 6. I can stop right there. That's imaginary. So therefore, it's not going to show up on the Cartesian coordinate system, which is real numbers. So no, can't use those numbers. Can I use the number 5? If I use the number 5, I get the square root of 0 over the square root of 12. Well, I know the square root of 12 exists. Does the square root of 0 exist? Sure it does, because 0 times 0 is 0. So the square root exists. I can't really draw the area because there is none. But I can use the number 5. Can I use the number -7? Well, -7 plus 7 is 0. The square root of 0 is 0, but that's a problem because I cannot divide a number, a 0 into a number. So no, I cannot use -7. Why did I put -1? All right, -7. There, that's better. All right. So I can't use that number. I can use this number. Can I use numbers between -7 and 5? Let's put a 0 in here. Does the square root of 5 divided by the square root of 7 exist? Absolutely, yes. We'll get something on a calculator. It looks like it'll be a little less than 1. All right. Can I use numbers less than -7, like -8? And for the reason I talked about before, no, the square root of -1 is actually what we call I. Talked about that in class quite a bit. So what was the domain of this problem? In this case, I saw that was a no. I think I would probably write this as an X less than or equal to 5, greater than -7. That would be your domain, and we'll practice that on a daily basis and hopefully get quick with doing that. That's really a 15-second question with enough practice. And we've already been talking about situations where we find the critical numbers. So let me just find them real quick. This is a V-shaped graph. If we do it visually with putting in a 0 gets us, well, first off, 4 gets you 7. And if I throw a 0 in here, I get 15, I believe. So a 0 gets me 15. And that's certainly not going to work. 0 doesn't work, but there is an X here and an X here. Right? Both of these X's are going to get us true, false, true from a graphical standpoint. All right, so let's just do it from a number line standpoint right now. So we find the critical numbers, subtract 7, 14, 7 plus 4, 11. 11 is critical. Check it. 11 minus 4, 7. 14 and 7 get you 21. That's 7 units to the right of 4. So I'm going to go 7 to the left, save myself some time. And now I'm going to check true, false, true. I know it's going to be true, false, true right there. So we're going to get -infinity to -3. We've already done these problems. Union 11 to infinity. We have mastered them. Some folks have, but most folks haven't. So we're going to practice that number line work. And we'll do 3 days of that. All right, I'll do 5 problems a night, give you 1 per quiz the next day. And hopefully we can master that pretty quickly. Going to ask you to learn some stuff dealing with cubics. And this may be the last thing that I cover. I'm not sure, but cubics, and we'll only do cubics with positive coefficients, because this is really not in the textbooks, but it should be. And so it should be very familiar. Minus b over 3a. So cubics come at you. Where's my trusty push cart right here? So let's get a better angle on what I'm going to talk about here. So there are 3 types of cubics that come with a positive coefficient. All right, always increasing. Let's turn that a little bit this way. A slope of 0 at the point of inflection, and decreasing. Those are the 3 situations that are coming your way. And we're going to just get a quick look at how to find out which one of these graphs and some information that goes with it. These are called local maxes and local minimums. Very easy to find. The rate of change at the point of inflection, easy to find, takes a little bit of memorization. So let's begin that process. So minus b over 3a. If I had a cubic that went through 0, 2, and 10, it would look like this, and the point of inflection occurs at 4, 0, 2, and 10. And it's the average of the roots. So there's a video on putting cubics in graphing form. If you want more information than I'm going to give you at the moment, cubics in graphing form. And also it's based on completing the cube. And I've got a number of videos that deal with this, as well as integration from a geometric perspective. So there's some real, I think, preliminary concepts that I'd like you to start considering, because that's one thing that causes so much trouble for students when they get to pre-cal and calc, is not having enough time to process other than memorizing for a test and moving on. Just doesn't seem to serve students well. So thinking about these concepts earlier on, it's a good thing. All right, so what do we have? Minus b over 3a, not hard to find. b minus 6, so 6 divided by 3 times 2 is 6. We find that 1, we're going to get a cubic with an x value of 1, getting us a y value of 2 minus 6. If you'll notice, that's 3 times an opposite, very similar to the quadratic, which is 2 times an opposite. I've got easy numbers to work with here. I'm only going to give you easy numbers. with these calculations. So right now, the point of inflection occurs at 1. Put a 1 in, you got 10 minus 7. What do we have? Minus 4, minus 11, minus 11 plus 10, negative 1. All right, so at 1, negative 1, we've got ourselves a point of inflection. All right, what's the rate of change at the point of inflection? Rate of change, c minus 3a8 squared. I'm going to erase this now so I get some room here. C is 10, so we got A, B, C, and D. So I've got 10 minus 3 times, we already got A is 1. Oh, sorry, 2. A is 2. And we just found H, right? So HK, point of inflection, we're going to call HK the same way we call HK the vertex of a quadratic. So that shouldn't be anything new for you. And 1 squared in this case is 1. So 10 minus 6 is 4. So I've got a function that's going up at 4 to 1 at this instant. All right. And I also know that negative 7 is my y-intercept. So I might as well get negative 7 in here. Negative 7, 0, negative 7. And I also know that I'm going up at 10 to 1 at that instant. So it's going to be 10 to 1, 4 to 1. So I've got a function that's always increasing if you put it in Desmos. Right, and there are no local maxes and no local mins. There are not going to be any of those because we got this type of function. So how would we know that without a calculator? Well, there's a couple of things, just like a quadratic formula. If you memorize this, and I'm going to have you memorize it, you're going to get a negative number inside the square root. And I'll talk more about, when it's time to start this topic. I'll include it on every worksheet. I mean, folks can just look at this, and some folks can pick this up in a day or two. But H, which is we just found out is 1, plus and minus. The positive is going to be the one on the right. The negative is going to be the one on the left for our work. We found that it was going up at 4 to 1. So that's going to be minus 4 divided by 3 times A, 3 times 2. And you can see that this is an imaginary number in the square root, which tells us we don't have any local maxes and mins. And that's going to be the X values. Okay. And that's good enough for us. At the Algebra 2 level, in a standard sequential course, you're going to study something called rational roots. You might do synthetic division. I don't teach synthetic division anymore, but it's historically something that folks did to speed up the calculation. I think it's more important to talk about the rates, putting these things in graphing form. And for the folks who, connect with this, I'll show you how to do that. For the folks that don't, probably won't be using it at all to grade an Algebra 1 class. But as far as your edification, yeah, it's important. It's important to start these conversations. All right, so the cubics will be, that's pretty much it. And that'll be a 3-day rapid fire 5 in about 2 weeks, I'm guessing. Right, maybe, no, I think I said I might do that last in terms of homeworks. But exponential functions, I gave you the memorization sheet the first week of class. I've asked you to memorize these values. I know a lot of folks haven't yet, but you're going to need to in order to get us to the rules of logarithms. So e to the negative 1.1 is approximately 1/3. E to the negative 0.7 and 1/2. You can pause the video and see those. So we're going to learn how to graph e to the x and e to the minus x. Very similar to the types of graphs that we've been doing thus far, except I'm going to standardize it. I'm going to make it a 3 to 1 ratio using the exponents 0 and 1.1. I'll do that for you right now over here. Let's get this out of the way. This will be a 3-day situation as well. All right, so these graphs can be done in 10 seconds or less. So e to the x I know is this. I'm going to do 3 to 1, whatever that distance is. I'm going to triple it. I'm going to get the constant. I know e to the 0 is 1, so I'm going to get a jump of 10. And then I'm going to get a jump of 30. When am I going to get that? At 5. And I'm going to get it when I do e to the 1.1 as a tripling. So what makes this 1.1 6.1? 6.1 minus 5 is e to the 1.1, which is 3 times 10 is 30. And so 30 plus 6 is here. And 10 plus 6 is 16. We're done. All right, and you'll get a chance to practice that at your own pace. I don't know why I duplicated this, but I'll make this one the inverse. So let's make it 2 minus x. Then I know I've got a 3 to 1 in the other direction. That's poorly drawn. 3 to 1 in the other, if I pick the right numbers. So that's the 0, that's the 1.1. So what makes 2 minus x 1.1? Well, I'm going to move the x to that side. I'm going to do 2 minus 1.1. That's not too bad, 0.9. So therefore 0.9 right here. 2 minus 0.9 gets me 1.1. So 21 plus 9, 30. And then if I make this a 0, which is 2, if I put that in, I get 7 plus 9, 16. Okay, and that's y equals 9. So how do you get from 9 to 16? Well, I think that's jumping out at me. And how do you get from 9 to 30, 21? Well, 7 times 3 is 21, plus 9, 30. All right, so if we can do the exponential, then we should be able to do the inverse, which is, it takes a little bit more practice. But I'll do one for you right now. Y equals 2 ln of x minus 5 plus 6, something like that. So x equals 5 is the asymptote. And then I want to do 2 ln of 1 plus 6. And then I want to do 2 ln of 3 plus 6. All right, so what makes it 1? 6. 6 makes it 1. The ln of 1 is 0. So 0 times 2 is 0. 6 gets me 6. And then ln of 3 is 1.1 times 2 is 2.2. 2.2 plus 6 is 8.2, provided I can make this the number 3. And so that's 8 gets me 8.2. Bumpity, 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 bumpity. We'll spend more time than that. All right. And I got plenty of videos that give you rapid fire 5 practice on that. I'll include those. All right. I'm flying. Yep. Just getting the conversation started. And then we want to get the rules of logarithms, which means we have to practice things like this for a little bit. What is the ln of 6? 2.71 to the what is going to get me close to 6. We want to do these without a calculator. And again, it comes back to these. All right. And the ones that I'm going to deal with is e to the 0.7 times e to the 1.1. E to the 0.7 is close to 2. E to the 1.1 is close to 3. And so therefore, what exponent? I think you can see it. You got 0.7, 1.1. So let me spell it out more clearly. 6 is equal to 2 times 3, which is equal to e to the 0.7, approximately e to the 0.7, e to the 1.1, which is rules of exponents, 0.7 plus 1.1, 0.7 plus 1.1, and that gets us approximately 1.8. All right, so approximately 2.7 of them, and it just gets us a feel. And then we can dive into the rules of logarithms after we practice this for a while. I'll spell those out. All right. So I was very proud in high school that I got the ln of A plus the ln of B is the ln of AB. Kind of what I just did here, by the way. But I had no clue what any of this meant. None. Got an A. Wonderful. I had no idea what I was doing. So we're going to start this early on so we can hopefully figure out what we're doing and why. And did I mention that everything that's been on test thus far, all those 73-point questions, 1 point per problem, still coming your way? Sine of 5 pi over 6. We've already started this in class. Pi, top half of the circle, breaking it up into 6 parts. Good drawings get good answers. Good drawings get good answers. So we start at 0 radius lengths. We go to 1 pi over 6. Pi over 6, 30 degrees. We'll talk more about it in class. Pi over 4, 45. And we want 5 pi over 6. So we go to that spot. That's 150 degrees, right? 360 all the way around. So we're going to have to develop this concept of a radian more carefully than I'm doing right now. But we've got people in class who can already do these things correctly. They can help you with the mechanics. So that's a half. That's 1. That's negative root 3 over 2. And what's the sine? The sine is the altitude divided by, so we have a reference angle of 30 degrees, right? But our angle is 150. So we're going to have to learn this language system. And opposite the angle divided by the hypotenuse, we've kind of already got the sine function defined. So we'll do that a little bit every day. Maybe about, I would guess about 2.5 weeks from now, you'll get that homework. Maybe 3 weeks from now. And then we'll learn how to, write these things very quickly. So why, obviously, if we can write them quickly, then every number has significance. So how do we measure this? We measure from the middle. Then we ask, how are we going up and down? Well, I can see 5. It's easiest to do the sine function, learning that first, although textbooks you had to do the cosine. It's actually easier to use the sine function because we'll find out it's just a linear function. So I want 1830 to act like that place on the circle because the height at that place on the circle is at a max. And I'm measuring from a max. So 1830 is going to act, it's going to match up with pi over 2. I guess I got to make that further out. Plus pi over 2. Right, I think we can see that I'm breaking this up into 2 parts. Pi 180, that's 90-degree angle, pi over 2 radians, 1.57 radius lengths. There's 1 radius length to about there. And then 0.57 more takes me to that place on the circumference. All right, so I guess I'm starting it here. So therefore, I basically finished it, but 1830 matches up with pi over 2. And what have I got? I've got 1830 to 1900. That's 70 years of change, but 1 revolution right there. So that means if I go from here to here, that's halfway around the circle. There's the other half. I'm starting from 90 degrees, but there's 1 pi, 2 pi, 3 pi takes me to a min. 1 pi, 2 pi, 3 pi takes me to a minimum. And so if I put 1900 in, there's 70s cancel, 3 pi, 1 pi. Well, I'm doing the sine function, so max to min, back to max, back to min. So that's -1. What's -1 times 5? -5, and 15 minus 5 gets me 10. Bingo. All right, and then the last thing we'll do with trig is a couple of simple equations. At some point during the second half, you'll realize that this is height, sine is height in the unit circle. And so you're basically saying, can you solve h times h minus 1 equals 0? Well, h equals 0 and h equals 1. Trying to learn how to solve those and then answer. We've gotten better at writing in factored form, but we're sometimes not answering what numbers work. So where are heights 0? Heights are 0 here and there, and where are heights 1 up there? So what are those 3 locations for x? 0 radians, no trip around the circle. Pi over 2 to get to the one at the top, and then pi to get over here. All those angles, 1 period worth of angles. That's a solution. And then we want to know that, when you're graphing the sine function, if we're talking heights, then your heights go up to the max, then they come back to 0, then they go to a -1, and then they come back again. And so that's your basic sine curve. So what does this one become? Well, this one becomes 10 is the center, up and down 4. So I've got 1 period of the sine function, positive sine function, looks like that. I start at 0, gets me 10. And then I know 0 is the start, 2 pi unit, 6.28 radius length. So when does 3x equal 2 pi? 2 pi over 3. Brings me back to 10. And then you got symmetry all over the place. So that'll be a unit of measurement for us, a unit of consideration. And then the last thing we're going to do is some very simple rational functions. Going to keep them extremely simple, just very straightforward. Things like, what does the graph of x minus 3 over x plus 2 look like. And when you first start these, they're troublesome. A lot of classes skip them now. Don't even study rational functions at the algebra 2 level. And that's crazy. So we start with just introduction to this stuff so that your brain can start processing things and have enough time to go, oh, I can figure that out. So fancy term, rational functions for what? Fraction. I'm going to give you fractional equations. Let's see if I can bring this over. Turn it this way. There we go. All right, so what do I immediately see? I see that the numerator and denominator are 5 units apart. All right, well, 5 units apart, I could have 5 and a third divided by a third. Well, those numbers are 5 units apart. Right? Actually, I wanted the smaller one on the top, bigger one on the bottom, but get the gist here. This could be, this actually 1/3 fits into that a lot of times. Versus put a million in. It's a million, 1,000 minus 3 over 1,002. Well, those numbers are actually pretty close together when we start talking about large numbers. They're only 5 apart, so that's going to get me close to 1 as a division. So just to show you what this is, when does that equal 0? When the numerator equals 0, so you're going to find the x-intercepts of these things. -2 makes this undefined, domain issue. You're going to get asymptotic behavior. When are you going to get asymptotic behavior? When you put a number like minus 1.999 in here. Because when you add that up, you get 0.001. And that's going to fit into, what did I take 2 away from this? I'm near -5. Okay, so we're going to have to get a feel for that. That goes into that a lot of negative times. Then I can certainly throw a 0 in here, -3/2. And I can quickly see that this thing has an asymptote of y equals 1. I don't expect you to follow this right now. Just putting it in your head. All right, and I know that there are no other x-intercepts other than 3. So this thing has got to look like that. And we'll take time with this in class, and that'll be one of your homeworks. And that's how we're going to approach the second half of the semester, 9 weeks of study. So every day you come in, worksheet. I'll highlight some aspect of what we're studying that week. So we'll start with those systems of equations and parallels, perpendiculars, and a little direct and inverse variation and joint variation, and up and running. And we'll try to get you as many considerations that you can understand before you leave the class in mid-December. All right, seems like an awful lot right now, but I think it's manageable, or I wouldn't be asking you to do it. All right, see you in class after the break.